Jupiter is the largest planet in our solar system, more than twice as massive as all the other planets combined. It is a sphere of hydrogen and helium, the same basic ingredients that make up the Sun, yet it orbits as a planet, not a star. This was not an accident. Jupiter's story takes us back to the earliest days of the solar system, to a time with no planets at all, only a cold, rotating disk of gas and dust surrounding the newborn Sun. What happened in that disk depended on distance from the star, temperature, the amount of material, and timing. Together, those factors built the object we see today. Tonight, we ask a simple question with a long answer. How did Jupiter become the giant we see today? To understand why Jupiter almost became a second sun, we do not begin with the planet itself. We begin earlier, before there were planets, before there were moons or rings, when the solar system was only a cold, rotating cloud of gas and dust. Long before the Sun settled into its present state, the region that would become our planetary system was a part of a larger molecular cloud in space. This cloud was mostly hydrogen gas, with some helium, and a smaller portion of heavier elements and tiny solid grains. It was cold, with temperatures only a few tens of degrees above absolute zero, and it was dark because there was no central star yet to light it from within. At some point, a small part of this cloud began to collapse under its own gravity. There may have been a nearby event that helped to start the collapse, such as the shock wave from an exploding star elsewhere in the galaxy. But whatever the exact trigger, gravity did the rest. As the cloud region fell inward, it spun faster because angular momentum is conserved. The material could not fall straight to the center. Instead, much of it flattened into a rotating disk around a growing, dense clump in the middle. That central clump would become the young Sun. The flattened structure around it is called a protoplanetary disk, a disk of gas and dust that orbits the newborn star. This disk is the birthplace of Jupiter and of all the planets. At first, the disk is mostly smooth. Gas moves in orderly, nearly circular paths around the center. Dust grains made of ice, rock, and metal collide gently and stick together. These grains are small, but over time they grow. The process is slow but steady. Tiny grains stick to form larger grains. Those larger grains grow into pebbles. Pebbles collide and form boulders. Each step is guided by simple physics. When two solids meet at low speed, electrostatic forces and surface effects can help them stay together. When an object becomes larger, its gravity begins to matter as well. As this growth continues, some regions in the disk gain a slight advantage. Perhaps the density of particles is a little higher, or the gas flow causes material to drift and collect. Where more solid material gathers, collisions happen more often, and growth speeds up. Over time, these regions give rise to planetesimals. A planetesimal is a solid body large enough that its own gravity holds it together, and large enough that it can begin to attract nearby particles and smaller bodies. These are the building blocks of planets. The part of the disk where Jupiter forms lies beyond what is called the snow line. This is the distance from the young Sun where temperatures are low enough for water and other volatile substances to freeze into solid ice. Beyond this line, not only rock and metal grains exist, but also abundant ice grains. Ice contributes more solid material, which means there is more mass available to build large cores. So, in the region that will become Jupiter's orbit, the protoplanetary disk contains a thick mix of gas and solid particles, including many icy pieces. In this colder, outer region, planetesimals grow more quickly in mass because there is simply more solid material per unit area of the disk. As planetesimals collide and merge, some become larger than the rest. These growing bodies begin to dominate their local zones. Their gravity increases, and with that, their ability to pull in more material. These growing seeds are called planetary embryos, and one of them, in the region beyond the snow line, becomes the core of what will be Jupiter. The growth of Jupiter's core is a process of accretion. Solid objects, from small ice grains to sizable planetesimals, are drawn in and added to the core. Each collision releases energy and heats the growing body, but the surrounding space is still cold. Over many hundreds of thousands and then millions of years, the core becomes more massive. Models of planet formation suggest that Jupiter's core reached a mass perhaps around 10 times that of Earth, though the exact number is still a topic of study and debate. The important point is that this core passed a critical threshold. It became massive enough that its gravity could not only attract solid material, but also begin to pull in large amounts of gas from the surrounding disk. At first, the gas around the core is nearly in balance with the rest of the protoplanetary disk. The core is surrounded by a small envelope of hydrogen and helium, heated by the energy of accretion and by compression. If the core is too small, this envelope stays thin and can be stripped away by the disk's motions or by radiation from the young sun. But once the core is heavy enough, its gravity holds on to the surrounding gas more strongly. The envelope grows denser and more extended. There is a feedback effect. A larger envelope has more gravity, which allows it to attract even more gas. When this process becomes rapid, we call it runaway gas accretion. As runaway gas accretion begins, Jupiter changes from being a mostly solid body with a thin gas layer to being a massive gas giant. The growing planet draws in hydrogen and helium gas from the disk at an increasing rate. The envelope thickens and deepens. The planet's total mass climbs far beyond that of its original solid core. In the end, Jupiter becomes more than twice as massive as all the other planets in the solar system combined. The bulk of this mass is hydrogen and helium, the same elements that make up most of the Sun. This is why, in composition, Jupiter is often described as a kind of failed star, or better, a nearly star-like object that did not quite reach the conditions needed to shine by sustained nuclear fusion. To see why Jupiter did not become a star, we need to look at what a star is. A star is a massive sphere of mostly hydrogen and helium in which pressures and temperatures at the center are high enough to fuse hydrogen into helium, releasing energy. This energy flows outward and balances the inward pull of gravity. The minimum mass for an object to ignite sustained hydrogen fusion in its core is much larger than Jupiter's mass. Even for a weaker process, such as the fusion of deuterium, a heavier form of hydrogen, a body must have a mass of at least about 13 times that of Jupiter. Jupiter never reached that mass. Its gravity, while strong, is simply not strong enough to compress and heat its core to the extreme conditions needed for steady fusion. So, Jupiter remained below the threshold for star-like behavior. It did contract as it formed, and it still slowly contracts today. As it does, it releases some heat. In fact, Jupiter emits more energy into space than it receives from the Sun because of this ongoing contraction and because of leftover heat from its formation. But this is not the same as the energy from hydrogen fusion that powers stars. The difference in mass is crucial. Gravity is the engine that tries to compress any large gas body. If the mass is large enough, the compression becomes intense enough to ignite nuclear reactions. If the mass is smaller, the object settles into a different kind of balance, supported by internal pressure without sustained fusion. We can imagine Jupiter in the context of a spectrum of objects in the universe. On the lower end, there are terrestrial planets, like Earth and Mars, made mostly of rock and metal, with thin atmospheres. Above them, in mass, are gas giants, like Jupiter and Saturn, made mostly of hydrogen and helium gathered around a core. Above them are brown dwarfs, which are more massive than Jupiter, but less massive than small stars, and may burn deuterium for a time, but not regular hydrogen. Above those are true stars, where hydrogen fusion becomes long-lasting. Jupiter sits below the brown dwarfs, firmly in the gas giant category. It is big for a planet, but small for a star. The reasons it stopped where it did are tied to the history of the protoplanetary disk. While Jupiter was growing, the disk itself was evolving. The young sun was bright in ultraviolet and X-ray radiation, and it produced a powerful solar wind. These effects gradually blew away the gas in the disk, especially in its outer layers. At the same time, accretion onto the sun removed material from the inner regions. Over a few million years, the gas in the disk thinned and then largely disappeared, leaving behind only the planets and smaller, leftover bodies. For Jupiter to grow into a much more massive object, it would have needed more time and more gas in its surroundings. Instead, its growth was limited by the available material and by the finite lifetime of the disk. Another factor is Jupiter's own influence on its environment. As Jupiter grew, its gravity began to affect not only local particles, but also the structure of the disk itself. The planet carved a partial gap in the disk where its gravity disturbed the gas. Material near the orbit interacted with the planet, creating waves and resonances in the gas. Some gas still flowed across the gap toward the inner disk, but the rate at which Jupiter could accrete new gas was reduced. The planet's own success in growing large began to limit the supply that could reach it. In this way, Jupiter helped to regulate its own maximum mass. At the same time, Jupiter's presence affected the orbits of nearby planetesimals and smaller planetary embryos. As the young gas giant's mass grew, its gravitational reach extended. It began to scatter smaller bodies, either drawing them in and absorbing them, or flinging them onto new orbits, some inward and some outward. Over time, this process helped to clear its orbital region. In planetary science, a planet is often defined not just by its orbit, but by its ability to clear that orbit of other debris. Jupiter does this very effectively. Its mass and gravity dominate a wide region of space around its path around the Sun. Clearing its orbit is not a single event. It is a continuing process that occurs over long timescales. Early on, Jupiter would have encountered many planetesimals and smaller objects in its vicinity. Some would have collided with the planet and been incorporated into its mass, adding to its core or entering its deep atmosphere. Others would have been deflected into elongated orbits that crossed paths with Saturn or other forming planets. Some would have been ejected from the solar system entirely, gaining enough energy from close encounters to escape the Sun's gravity. Through these many interactions, Jupiter helped to shape the architecture of the solar system we see today. Because of its mass, Jupiter also plays an important role in stabilizing the orbits of other planets to some extent. Its gravitational pull perturbs asteroids and comets. It contributes to resonances in the asteroid belt, where repeated gravitational tugs from Jupiter can clear certain orbits and concentrate material in others. It may have reduced the number of frequent large comet impacts on the inner planets by scattering many icy bodies out of the inner system, though the details are complex and involve trade-offs between delivering impactors and removing them. In any case, Jupiter's presence has been a major factor in the long-term dynamics of small bodies. It is useful to pause and recall where we are in this story. We began with a cold molecular cloud. Gravity caused part of that cloud to collapse into a young star, with a disk of gas and dust. Within that disk, solid grains collided and stuck together, forming planetesimals. In the outer part of the disk, beyond the snow line, icy material added to rocky cores, allowing them to grow large. One such core reached enough mass to pull in a huge envelope of hydrogen and helium. This process created Jupiter, a gas giant that almost had enough mass and pressure to ignite brief nuclear fusion, but did not. And that helped to clear its orbit and become the dominant object in the solar system after the Sun. The phrase that Jupiter almost became a second sun reflects its composition and its size, but it must be understood carefully. Jupiter is made of mostly the same raw materials as the Sun. It forms in the same collapsing cloud and from the same disk. It is a sphere of gas with a deep gravitational well. It produces internal heat and radiates that heat into space. All of these traits resemble those of a star, yet the differences are just as important. Jupiter's mass is too small. Its core, while hot and dense in absolute terms, does not sustain the extreme temperatures and pressures required for steady hydrogen fusion. While the Sun shines steadily for billions of years by converting hydrogen to helium, Jupiter glows only faintly in infrared, cooled and powered by contraction and residual formation heat. This distinction helps inform our understanding of how varied objects in the universe can be. There is not a sharp, sudden boundary between planets and stars when we consider their formation. There is a continuous range of masses and outcomes, and the details of each system's initial conditions matter. In our solar system, The largest object that formed in the disk was the Sun at the center. The next largest is Jupiter, which took the role of a massive planet rather than a small star. If the disk around the young Sun had been more massive, or if conditions had allowed Jupiter to accrete for a longer time before the gas vanished, it might have moved further along that range. But with the conditions that actually existed, Jupiter ended up where it is, the biggest planet, not a star. Jupiter's sheer scale is still astonishing when we compare it with other planets. Its diameter is more than an order of magnitude greater than Earth's, and its mass is more than 300 times larger than our planet's mass. Yet it is still less dense overall, because it is made mostly of light gases compressed under gravity. The planet's rapid rotation gives it an oblate shape, slightly flattened at the poles. Its strong gravity compresses its interior to enormous pressures, and its deep atmosphere hides layers that we cannot see directly with ordinary telescopes. These features remind us that, although Jupiter is not a star, it is far from a simple object. The early history of Jupiter also includes interactions that differ from simple, static pictures. Some models suggest that Jupiter may have migrated inward and then outward within the disk during its formation, influenced by gravitational interactions with the gas and with other massive bodies. In such scenarios, Jupiter does not form exactly where it is now, but moves through the disk before settling into its present orbit. If this occurred, then Jupiter's effect on the distribution of material in the inner solar system and on the formation of terrestrial planets could have been even more pronounced. While details of this migration are still under study, the key idea is that Jupiter's gravity did not act only locally, but had a wide reach across the evolving disk. Over time, as the protoplanetary disk dispersed and the Sun reached a more stable phase, Jupiter's growth slowed and then stopped. With no more surrounding gas to accrete in large amounts, the planet's mass froze at its near final value. From that point on, its evolution became mainly internal. It cooled, contracted slightly, and settled into a long, slow decrease in internal temperature. The surface we see now in images, with bands and storms, is the top of a deep atmosphere shaped by rotation, heat flow from the interior, and solar radiation from above. From the perspective of planet formation theory, Jupiter is a textbook example of how a gas giant can form in a planetary system. Yet it is also a reminder that the outcome depends on both the mass of the forming core and the lifetime and mass of the disk. In systems where the disk is more massive, or where cores form very quickly, gas giants might grow more massive and perhaps cross the boundary into brown dwarf territory. In systems with lower mass disks or with less efficient core growth, gas giants might never form at all. Our solar system sits somewhere in between, with one very large gas giant and several smaller ones, but no second star. As we move forward in our exploration of Jupiter, the next question becomes more detailed. We have followed the story of how the planet formed from the disk, gathered its mass, and settled into its orbit as the largest world after the Sun. This explains why it is so big and why it almost, but not quite, reached star-like conditions. What remains is to understand what this mass and composition create inside the planet itself. Beneath the colorful cloud tops that we can see, there are layers of gas, liquid, and perhaps exotic forms of hydrogen under extreme pressures. Now, we move from Jupiter's birth in the protoplanetary disk to Jupiter's hidden interior, and we ask what lies beneath the clouds of this almost star-sized planet. The visible face of Jupiter is a layer of clouds that floats at the top of a deep and complex atmosphere. When we speak of the cloud tops, we are really talking about the level where the pressure in the gas is similar to the air pressure at the surface of Earth, and where the atmosphere becomes opaque in visible light. Sunlight comes in, scatters off these clouds, and returns to space. That is what telescopes and spacecraft cameras see. Above this level, the gas is thinner and more transparent. Below it, the gas becomes denser, warmer, and darker. The bright bands and darker belts that we see on Jupiter are patterns in this topmost weather layer, but they are only the surface expression of a much deeper system. Jupiter's upper atmosphere is made mostly of hydrogen and helium gas, the same basic mixture that makes up the Sun. Mixed into this light gas are small amounts of water, ammonia, methane, and other simple molecules that contain oxygen, nitrogen, sulfur, and carbon. Although these trace components are minor in mass, they control much of the visible appearance. At certain heights and temperatures, they condense into clouds made of tiny droplets or crystals. In particular, ammonia condenses high in the atmosphere, forming the uppermost cloud deck. Deeper down, where it is warmer, other cloud layers form, including clouds that likely contain water and compounds of sulfur and ammonia. Each cloud layer has its own typical altitude range, and together they create the structured, banded look that we see. Above the visible cloud tops, there is more to the atmosphere. There is a thin stratosphere where temperature stops decreasing with height and then begins to increase again. Warmed by absorption of solar ultraviolet light and by emission from molecules such as methane and hydrocarbons that sunlight helps to form. Even higher is a thermosphere, where the gas becomes very hot, not because of a dense heat source, but because a small number of particles gain a lot of energy from solar radiation and from interactions with charged particles in Jupiter's magnetic field. These upper layers are extremely tenuous. Their particles are far apart. They play an important role in the planet's auroras and in its interaction with the solar wind, but they contain very little mass compared with the deeper layers. When we move downward from the visible clouds, the story changes. The pressure begins to rise steadily because more and more gas lies above. Gravity pulls inward on this gas, and the gas must support the weight of the layers above it. This balance is called hydrostatic equilibrium. As we descend, the gas is compressed and warms. This pattern of increasing pressure and temperature with depth is also present in Earth's atmosphere. But on Jupiter, it continues far deeper and reaches much higher values. Within a relatively shallow distance below the cloud tops, the pressure multiplies, the gas thickens, and the familiar idea of separate clouds and clear sky gradually gives way to a more continuous medium. In the region just below the visible ammonia clouds, we encounter a second cloud layer, thought to consist of ammonium hydrosulfide. This substance forms when ammonia and hydrogen sulfide combine at the right temperature and pressure. These clouds, if we could see them directly, would likely have different colors and textures from the upper ammonia clouds, and they contribute to some of the browns and reds in Jupiter's belts and zones. Deeper still, where the temperature is higher again, water vapor condenses and forms thick water clouds. Water is heavier and more abundant among the oxygen-bearing species, so this cloud layer may be quite massive. Below the water clouds, the gas may become relatively cloudy throughout, with fewer clearly separated decks. At some depth, the distinction between discrete clouds and surrounding gas becomes less meaningful. The atmosphere transitions from a place with visible cloud structures into a deep convective region. In this region, rising and sinking motions transport heat from the interior toward the surface. Warm gas rises, cools as it expands, and then sinks again once it has lost enough heat. This overturning is a key part of Jupiter's weather and contributes to the formation of storms and jet streams near the top of the atmosphere. The energy that drives this convection comes not only from sunlight, but also from Jupiter's own internal heat, which is significant. As we continue downward, the pressure grows very large. The gas becomes so compressed that hydrogen, which is a light and simple molecule, begins to behave in unfamiliar ways. In the upper atmosphere, hydrogen exists mainly as pairs of atoms bound together, called molecular hydrogen. Under increasing pressure and temperature, these molecules are squeezed closer together. Eventually, at great depths, the molecules break apart, and the hydrogen enters a state in which electrons are no longer bound to individual atoms in the usual way. The hydrogen becomes a dense fluid that can conduct electricity almost as well as a metal. This state is called metallic hydrogen. Metallic hydrogen does not mean that hydrogen suddenly turns into a solid metal like iron. Instead, it refers to the way electrons in the material move. In a metal, electrons are free to travel through the structure, which allows metals to conduct electricity and heat efficiently. In the high-pressure interior of Jupiter, the hydrogen is probably in a form that is closer to a liquid than a solid, but its electrons move freely enough to give it metallic properties. Experiments on Earth can briefly create metallic hydrogen using extreme pressures, and theoretical models support the idea that such a state exists inside gas giant planets. The pressures needed are many millions of times the air pressure at Earth's surface, and the temperatures are thousands of degrees. The transition from molecular hydrogen to metallic hydrogen inside Jupiter is likely not a sharp boundary. It is probably a gradual change over some range of depth, where the properties of the hydrogen blend from one regime into the other. At shallower depths, the hydrogen is a dense molecular fluid. At deeper levels, the metallic behavior dominates. The exact details of this transition are still being studied, using a combination of laboratory work, high-pressure physics, and careful analysis of data from spacecraft that measure Jupiter's gravity field and magnetic field. We do not have direct samples from these depths, so our knowledge is indirect. But the basic picture of a metallic hydrogen layer is widely supported. This metallic hydrogen is central to Jupiter's role as a magnetic planet. To generate a large magnetic field, a planet needs three main ingredients. There must be a region of electrically conducting material. That region must be in motion, usually in the form of convection, driven by heat. And the planet must be rotating, so that the motions favor organized patterns that can sustain a magnetic field. This process is called a dynamo. On Earth, the conducting region is the liquid outer core, made mostly of iron and nickel, moving slowly under the influence of heat from the interior. On Jupiter, the conducting region is the thick layer of metallic hydrogen, which stretches through a large fraction of the planet's interior. Within this metallic hydrogen layer, heat from deeper inside the planet drives convection. Hotter, less dense material rises. Cooler, denser material sinks. These motions, combined with Jupiter's rapid rotation, twist and stretch magnetic field lines. The result is a strong global magnetic field that, near the planet, is more intense than Earth's field by a large factor. The field is roughly dipolar, with a north and south magnetic pole. But it is tilted relative to Jupiter's rotation axis and has more complex structures as well. Spacecraft have measured irregularities and higher-order components in the field, giving clues about the flow patterns and the depth of the dynamo region. The magnetic field of Jupiter extends outward to form a vast magnetosphere, which is the region where the planet's magnetic influence dominates over the solar wind. This magnetosphere is filled with charged particles, many of which come from volcanic activity on the moon Io and from the solar wind itself. These particles spiral along magnetic field lines, collide with each other, and interact with the thin gas around the planet. When particles follow field lines into the polar regions and strike Jupiter's upper atmosphere, they produce auroras, rings of glowing emission in ultraviolet and visible light. These auroras are persistent and powerful, much stronger than typical auroras on Earth. They are another sign of the strength of Jupiter's magnetic environment. Closer to the planet, within the magnetosphere, charged particles become trapped and form radiation belts. These belts surround Jupiter and present a harsh environment for spacecraft and for any object that spends time there. The radiation in these belts can damage electronics and materials, so missions to Jupiter must plan trajectories and shielding carefully to reduce exposure. These belts are somewhat similar in concept to Earth's Van Allen belts, but they are more intense and extensive. The existence of such radiation belts again points back to the underlying cause, which is the combination of a strong magnetic field and a source of energetic charged particles. While the deep interior and the metallic hydrogen dynamo are hidden from direct view, Jupiter's weather is displayed openly in its upper atmosphere. The alternating bands of light and dark that encircle the planet are called zones and belts. Zones are usually brighter and appear whitish or pale, while belts are darker and more brown or reddish. These patterns are not fixed like stripes on a solid surface. They are regions where winds flow in opposite directions. In many places, the winds in a zone move eastward, while the winds in the neighboring belts move westward or the other way around. These alternating jet streams wrap around the planet and are very fast compared with typical winds on Earth. The bands and jets create a stable, large-scale pattern, but within that pattern, there is constant activity. Convection from the interior brings heat upward. As parcels of gas rise and fall, they form storms, plumes, and vortices. Some of these features last for a short time, others for much longer. Ammonia and other cloud-forming substances are carried up and down, changing local cloud thickness and color. Sunlight and chemistry in the upper atmosphere gradually alter some of the molecules, producing complex compounds that may contribute to the varying hues that we see. As a result, Jupiter's appearance changes over time. Bands can widen or narrow, become more or less distinct, and occasionally show disturbances that move along their lengths. One of the most famous features of Jupiter's weather is the Great Red Spot. This is a large storm system located in the southern hemisphere, within one of the major belts. When viewed from above, it appears as an oval region of reddish color, larger than Earth in diameter. It has been observed for centuries, making it a long-lived atmospheric phenomenon. The Great Red Spot is an anticyclone, meaning that it is a high-pressure system where winds flow around a central region in a clockwise direction in the southern hemisphere. The winds are strong, with speeds that exceed those of typical hurricanes on Earth. But the storm is confined to a certain altitude range and to the layer of clouds that we can see. The persistence of the Great Red Spot is a sign of how different Jupiter's atmosphere is from that of terrestrial planets. There is no solid surface to disrupt the storm. There is also a continuous supply of energy from deeper convection and from interactions with nearby jet streams. The storm sits between bands of different wind speeds, and these shearing flows may help to maintain its circulation. Over the time that we have seen it, the size and color of the Great Red Spot have changed. It has gradually become smaller in recent decades, and its hue has varied from deep brick red to more pale shades. These changes suggest that the storm is not fixed in a rigid way, but responds to shifts in the broader atmospheric system. Beyond the Great Red Spot, Jupiter hosts many other storms and vortices. Some of these appear as smaller red or white spots that drift through the belts. Others are clusters of thunderstorms that rise as bright plumes and then spread out. Lightning has been detected in Jupiter's clouds, indicating strong convective activity, especially in regions associated with water clouds deep in the atmosphere. These storms release energy and redistribute heat and material. They also interact with the surrounding jet streams, contributing to the continuous reshaping of the banded pattern. The overall effect is that Jupiter's atmosphere remains in a state of dynamic balance, where large-scale structure persists, while small and medium-scale features constantly emerge and fade. The vertical structure of Jupiter's weather is also important. The top of the visible clouds marks a certain pressure level, but storms and motions extend above and below this. Some convective towers rise to higher altitudes, producing bright spots in ultraviolet and infrared observations. Other motions penetrate downward, mixing material between the cloud layers. Temperature profiles measured by spacecraft and from Earth-based observations show that the atmosphere is cooler near the cloud tops and warmer both above, in the stratosphere, and below, in the deeper troposphere. This structure reflects the combined influence of solar heating, internal heat flow, and radiative cooling. Jupiter's rapid rotation plays a central role in organizing its weather. The planet completes one spin in less than half an Earth day. This fast rotation strengthens the Coriolis effect, which is the apparent force that deflects moving air in a rotating frame. On Jupiter, this effect causes rising and sinking motions to align into narrow bands, and it favors the formation of long, parallel jet streams rather than large, unstructured flows. The balance between pressure gradients, Coriolis forces, and drag leads to the zonal wind pattern that we observe. In this way, the rotation connects the interior dynamics, which supply heat, with the large-scale atmospheric motions, which shape the appearance of the clouds. Deeper down, below the layers where sunlight has direct influence, the atmosphere gradually transitions into the broader interior. At some point, hydrogen and helium stop behaving as a thin gas and form a dense fluid. The concept of separate atmosphere and interior becomes less useful because there is no sharp boundary like a solid surface. Instead, the planet is a continuous envelope that gradually changes in properties as depth increases. The upper regions are transparent to visible light and host weather. The middle regions are dense and hot, carrying heat often by convection. The inner regions become metallic and support the dynamo that generates the magnetic field. Near the center of Jupiter, there may be a core made of heavier elements, such as rock and ice, or a region where these heavy elements are mixed into the surrounding metallic hydrogen. Data from the Juno spacecraft suggests that Jupiter's core might be diffuse and extended, rather than a small, sharply defined ball. This could be a result of the way Jupiter formed, including possible collisions with large planetesimals or early mixing processes during rapid growth. In any case, the exact structure of the core is still being refined. What is clear is that the overlying layers of hydrogen and helium are so massive and so compressed that they dominate the planet's volume and many of its key properties. The picture that emerges from these considerations is that Jupiter is a layered but continuous system. At the top, clouds and storms are shaped by rotation, convection, solar heating, and internal heat. Below, the gas becomes denser and hotter, supporting strong winds and complex flows. Deeper still, hydrogen changes state, becoming metallic and forming an electrically conducting shell that, in motion, generates a powerful magnetic field. At the center lies a reservoir of heavier material, whose exact form remains an active research topic. All of this operates over billions of years, with slow changes in the interior and more rapid changes in the weather above. This complex interior and atmosphere do not exist in isolation. They sit within a strong gravitational field that governs the motions of many other objects nearby. Jupiter's mass, rotation, and magnetic field together create an environment that extends far beyond the planet's visible disk. Within this environment orbit dozens of moons, ranging in size from small, irregular bodies to large worlds with their own internal activity and atmospheres. The interaction between Jupiter and its moons involves gravity, tidal forces, magnetic connections, and exchanges of material. From the deep metallic hydrogen that powers the magnetic field to the storms that churn in the upper clouds, Jupiter shapes and is shaped by the system that surrounds it. The next step in the story is to follow that influence outward and examine the family of moons that revolve around this almost star-sized planet, and to see how Jupiter's presence has affected their surfaces, interiors, and histories. Jupiter's family of moons forms within the same overall story of gas, dust, and gravity that shaped the planet itself. While Jupiter is gathering its thick envelope of hydrogen and helium from the protoplanetary disk around the young sun, a smaller disk forms around Jupiter. Gas that falls toward the growing planet carries angular momentum, which means it cannot simply fall straight in. Instead, it spreads out and settles into orbit around Jupiter, forming a circumplanetary disk. Within this smaller disk, conditions resemble those of the larger solar nebula in miniature. There is gas, there are solid particles, there is a temperature gradient from the hot inner regions close to Jupiter to the cooler outer regions farther away. This is the environment in which many of Jupiter's regular moons form. In the warmer inner part of the circumplanetary disk, only rock and metal solids can remain stable. Ice cannot survive at these temperatures. Farther out, where the disk is cooler, water and other volatile substances can freeze and become solid grains. As in the solar nebula, these grains collide and stick, forming larger and larger bodies. Over time, small moonlets grow, clear their local orbits within the disk, and merge into larger moons. The result is a set of satellites whose compositions and densities reflect their birthplaces. Moons that form closer to Jupiter tend to have more rock and less ice. Those that formed farther out contain more ice mixed with rock. While many smaller moons and irregular objects around Jupiter have more complex histories, possibly involving capture, the four largest regular moons, called the Galilean moons, bear clear marks of having formed within this circumplanetary disk. The Galilean moons, discovered by Galileo Galilei in the early 17th century, are Io, Europa, Ganymede, and Callisto. They orbit Jupiter in order of distance, with Io closest, followed by Europa, then Ganymede, and Callisto farthest of the four. Each one is a sizable world. Ganymede is larger in diameter than the planet Mercury. Io and Europa are slightly smaller than Earth's moon, and Callisto is similar in size to Mercury. Yet, although they share the same primary planet and formed in the same general period, their surfaces, interiors, and activity levels are very different. These differences are not random. They arise from a combination of composition, distance from Jupiter, and the tidal forces that Jupiter exerts on each moon. Io, the innermost of the four, is a rocky world with very little ice. Its surface is dominated by volcanic features, lava flows, and deposits of sulfur and sulfur dioxide. There are almost no impact craters visible. This tells us that the surface is young because volcanic resurfacing erases old craters. Observations from spacecraft show active volcanoes erupting large plumes of gas and dust, some reaching high above the surface. Io is one of the most volcanically active bodies in the solar system. The source of this activity is not radioactivity in its interior alone, as in many rocky planets, but strong tidal heating from Jupiter's gravity. To understand this tidal heating, we consider how gravitational pull changes across a moon. The side of Io closer to Jupiter feels a stronger pull than the side farther away. This difference stretches the moon slightly along the line toward Jupiter. If Io orbited in a perfectly circular path and rotated in a steady way, this tidal bulge would be nearly constant in position, and the moon's interior would deform only slightly and remain mostly stable. However, Io's orbit is not exactly circular. It is slightly elliptical. As Io moves closer to and farther from Jupiter during each orbit, the strength and direction of the tidal pull change. The tidal bulge shifts and flexes. The solid interior of Io is stressed and squeezed repeatedly. This continual flexing produces friction and heat inside the moon, which melts rock and drives volcanic activity. Europa orbits just outside Io and is somewhat smaller. Its surface is very different. Instead of bright volcanic plains, Europa shows a smooth, bright icy shell crisscrossed by long, linear features. These features, called lineae, are bands and ridges formed by the cracking and shifting of the ice shell. Impact craters are rare, suggesting that the surface is relatively young on geological timescales. Beneath the ice crust, evidence indicates that there is a global ocean of liquid water or warm, slushy ice. This evidence comes from several lines of observation. The way Europa's surface flexes under Jupiter's gravity, the magnetic response measured by spacecraft, and the surface geology that implies movement and exchange between layers. The tidal forces that act on Europa are weaker than those on Io, because Europa is farther from Jupiter and its orbital eccentricity is smaller. Even so, the tides are still significant. As Europa orbits, its shape changes slightly, and its interior is flexed. This generates heat, though less intensely than in Io. In Europa's case, the heat is enough to keep a deep layer of water from freezing completely solid. The ice shell above acts as a lid, insulating the ocean. The thickness of this shell is still uncertain, but models suggest it might be several tens of kilometers thick, with an ocean below that is perhaps similar in depth to or deeper than the oceans on Earth. The surface ice can crack, spread, and sometimes allow material from below to come up, while surface material can move downward. The overall picture is of a differentiated body with a metallic core, a rocky mantle, a liquid water ocean, and an icy crust, all shaped by tidal heating, balanced with the loss of heat to space. Ganymede, the next moon outward, is the largest moon in the solar system. It is bigger in diameter than the planet Mercury, though less dense because it contains a higher fraction of ice. Ganymede's surface shows two main types of terrain. There are older, darker regions that are heavily cratered, and somewhat younger, lighter regions with grooved patterns that indicate tectonic deformation. This mix suggests a history where the outer ice shell has been reshaped in some areas, while other areas have remained relatively unchanged. Like Europa, Ganymede appears to have an internal ocean layer beneath its ice shell, although its structure may involve several stacked oceans separated by ice layers at different pressures and compositions. One particularly notable property of Ganymede is that it has its own intrinsic magnetic field, generated by motions in a liquid, electrically conducting layer in its interior, likely a metallic or salty ocean, or a partially molten core. This means that, in addition to being embedded in Jupiter's large magnetosphere, Ganymede carries a smaller magnetosphere of its own. The interaction between these fields creates complex patterns of charged particle motion and auroral activity near Ganymede. The presence of an internal magnetic field tells us that, at least in the recent geological past, Ganymede has had enough internal heat and convective motion in its conducting layer to sustain a dynamo. Callisto, the outermost of the four, presents a different case. Its surface is dark and heavily cratered, with no obvious signs of recent geological reshaping. The craters are preserved over long times, forming a record of impacts dating back to the early solar system. Callisto's density suggests a mixture of rock and ice in roughly similar proportions. Unlike Ganymede, Callisto appears to be only partially differentiated, meaning that its interior is not fully separated into distinct core, mantle, and outer shell layers. Data from spacecraft provide hints that Callisto may have a subsurface ocean as well, inferred from its response to Jupiter's magnetic field. But if such an ocean exists, it is likely deeper beneath the surface and less active in shaping the outer layers than the oceans of Europa or Ganymede. These four moons, from the volcanically active Io to the quiet, cratered Callisto, illustrate how tidal forces and distance from Jupiter can lead to very different outcomes. The key to their differing levels of activity lies in how much tidal energy they receive and how that energy is stored and dissipated. Io, being closest, experiences the greatest tidal forces. Europa, being somewhat farther out, feels weaker forces, but still enough to maintain an ocean. Ganymede, larger and even farther away, has tidal heating that is weaker still, but still sufficient for an internal ocean and some past tectonic activity. Callisto, at the largest distance, experiences the weakest tidal forces among the four and appears largely geologically quiet at the surface. The tidal forces themselves are not fixed. They depend on the shapes of the moon's orbits. Those shapes are in turn affected by gravitational interactions among the moons. Io, Europa, and Ganymede participate in a gravitational pattern called a resonance. For every orbit Ganymede completes, Europa completes roughly 2, and Io completes roughly 4. This three-body resonance keeps their orbital periods locked in simple ratios. As a result, their orbits are prevented from becoming perfectly circular. Gravitational tugs at regular intervals maintain small eccentricities. These small deviations from circular motion are crucial because they keep the tidal flexing ongoing. If the orbits were allowed to circularize completely, the tidal heating would gradually die down, and the moons would cool and become less active. In this way, Jupiter's gravity and the mutual interactions between the moons act together to sustain long-term energy sources inside these worlds. Io's interior remains partially molten, and its surface remains volcanically active because tidal forces continue to knead it. Europa's ocean remains liquid because tidal heating supplies more energy than would be available from radioactive decay alone. Ganymede's internal layers remain warm enough to host a deep ocean and possibly maintain a magnetic field. Callisto, outside this resonance, does not receive the same continuous tidal input and has likely cooled more thoroughly, resulting in less internal activity and a more static surface. The roles of Jupiter's magnetic field and radiation environment further influence these moons. Io, for example, loses material from its volcanoes into space. Some of this material becomes ionized and is captured by Jupiter's magnetosphere, forming a torus of charged particles around the planet near Io's orbit. These particles, in turn, can impact the surfaces of the moons or contribute to auroral emissions. Europa, Ganymede, and Callisto experience varying levels of charged particle bombardment, which can alter their surface ices and drive simple chemical changes. These processes happen over long timescales and add another layer of interaction between the planet and its satellites. Beyond the Galilean moons, Jupiter hosts many smaller moons of varied origins. Some inner small moons orbit close to the planet and may be remnants of the circumplanetary disk or fragments of larger bodies. Many outer moons follow more inclined or retrograde orbits, suggesting that they are captured objects, perhaps originally asteroids or Kuiper belt bodies that were snared by Jupiter's gravity. Together with the rings, which are faint compared with the bright rings of Saturn, but still present, these moons and small bodies form a complex system. Jupiter is not just a single planet. It is the center of a miniature planetary system within the larger solar system. In the present era, Jupiter and its moons have reached a kind of long-term balance. The planet rotates rapidly. Its interior slowly cools. Its magnetic field continues to function, and its moons orbit in patterns that change only slowly over time. Volcanic eruptions on Io, resurfacing of Europa, gradual evolution of Ganymede's interior, and the quiet preservation of ancient craters on Callisto all proceed on their own timescales, influenced by the steady pull of Jupiter and the distant warming of the Sun. But this picture will not remain the same forever. On very long timescales, the Sun itself changes, and these changes will affect Jupiter and its system. The Sun is currently in the stable phase of its life, called the main sequence, during which it fuses hydrogen into helium in its core. This phase lasts for many billions of years in total. The Sun is roughly halfway through this span. Over the remaining time in the main sequence, the Sun will slowly brighten, and its outer layers will change modestly. These gradual changes will have some effects on planetary climates, especially on the inner planets. But Jupiter, at its greater distance, will experience only slight changes in the amount of sunlight it receives. Its internal heat will remain an important contributor to its atmospheric dynamics. The moons, especially those with subsurface oceans, will continue to evolve under the combined influences of Jupiter's tides and the distant Sun's light. Eventually, however, the hydrogen in the Sun's core will be depleted to the point where fusion in the core can no longer sustain the same structure. The Sun will leave the main sequence and enter the red giant phase. In this stage, hydrogen fusion moves to a shell around the core, and the outer layers of the Sun expand and cool. The Sun will become larger in radius and more luminous, although its surface temperature will be lower. The inner planets will be subjected to far more intense solar radiation. Mercury and Venus will almost certainly be engulfed or stripped of their current structures. Earth's surface conditions will be drastically altered long before any direct engulfment. Jupiter, located much farther out, is not expected to be engulfed by the Sun's expanded envelope in most models. Instead, it will see a significant increase in the amount of radiation it receives as the Sun's luminosity rises. Its upper atmosphere will warm, changing its temperature profile and possibly altering its clouds and weather patterns. At the same time, the Sun will lose mass through strong stellar winds and through the shedding of its outer layers. As the Sun loses mass, its gravitational pull on the planets decreases. In response, the planetary orbits expand. Jupiter's distance from the Sun will grow, although it will remain gravitationally bound as long as the mass loss is not too extreme or too rapid. The combination of increased luminosity and increasing orbital distance creates a complex pattern of changing conditions for Jupiter. For a time, the outer solar system may be warmer in terms of sunlight than it is today. This could modify the atmospheres of the gas giants and the surfaces of their moons. For example, ices on the surfaces of some moons may become less stable, leading to increased sublimation. Thin atmospheres or transient atmospheres might form in places where none exist today. The details of these changes depend on the exact path of the Sun's red giant evolution, which involves processes that are still being refined in stellar models. What remains robust is the expectation that Jupiter will survive this phase and remain a large planet orbiting the evolving Sun. After the red giant phase, the Sun will shed its outer layers more completely, forming a planetary nebula, a glowing shell of gas that expands into space. The exposed core of the Sun will contract into a white dwarf, a dense stellar remnant that no longer carries out fusion in its interior, but shines from residual heat. This white dwarf will have a mass somewhat less than the Sun has today, and a radius similar to that of Earth. Its gravitational field will still hold on to the remaining planets, but the overall structure of the solar system will be different. The bright, extended red giant will be gone, replaced by a small, hot, slowly cooling white dwarf at the center. In this new configuration, Jupiter will be a cold gas giant, orbiting a white dwarf star. Its atmosphere will no longer receive the same level of external heating from the Sun that it does now. Instead, the dominant source of energy in the planet's interior will be the remaining heat from its formation and the slow contraction of its mass, processes that are already operating today, but will become relatively more important once stellar illumination declines. Over very long spans of time, Jupiter's interior will continue to cool, and its atmospheric activity will gradually diminish in intensity. Its belts and zones, storms and jets will still exist as expressions of atmospheric dynamics, but they will evolve in response to the reduced sunlight and changing thermal structure. The moons of Jupiter will remain bound to the planet, barring very unlikely close encounters with other massive bodies. Their tidal interactions will continue, although some parameters may change slightly as Jupiter's orbit and rotation respond on long timescales to the changing gravitational environment. Subsurface oceans, if still present, will eventually cool as tidal heating and internal heat sources decline. Surface conditions on icy moons will become even colder than they are now, as the distant white dwarf provides only faint light compared with the present sun. The outer solar system will become a place of dim illumination, where planets and moons are lit mainly by the residual glow of the white dwarf and by reflected light from each other. Over even longer spans of time, additional slow processes can act. Gravitational encounters between planets or passing stars could perturb the orbits of the outer planets. Very rarely, such interactions could alter orbits enough to eject a planet from the system or move it to a much different distance. For Jupiter, the probability of such drastic events within the remaining lifetime of the galaxy is small, but not zero. Still, in many scenarios, Jupiter stays as a stable companion to the white dwarf remnant of the Sun, orbiting at an expanded distance compared with today, but still gravitationally tied. In this distant future, Jupiter will no longer be a planet warmed by a main sequence star. It will be a cold mass of hydrogen and helium, with a cooled interior and a subdued magnetic field circling a faint stellar core. Yet its basic identity as the largest planet in the system will remain. Its mass will still dominate the planetary population. Its gravitational influence on any remaining minor bodies will continue. The fossils of its former weather, interior structure, and moons will still tell a story to any observer who can reconstruct it. When we look back over the full story of Jupiter, a consistent picture emerges. In the early solar system, Jupiter forms in a region rich in gas and ice beyond the snow line, growing a rocky and icy core that becomes massive enough to draw in large amounts of hydrogen and helium. This growth stops short of the threshold needed for sustained nuclear fusion. Jupiter does not become a star. Instead, it settles into its role as a gas giant, with a deep atmosphere, a layer of metallic hydrogen, and a strong magnetic field generated by motions in its conducting interior. Around it, a circumplanetary disk forms, from which a system of moons emerges, including the 4 large Galilean satellites, each with a distinct balance of rock, ice, internal heat, and tidal activity. Jupiter's mass and gravity shape the paths of asteroids and comets, influence the formation of other planets, and sustain tidal heating in its moons. Io remains volcanically active under intense tidal flexing. Europa maintains a subsurface ocean beneath an icy crust. Ganymede carries its own magnetic field and signs of internal layering. Callisto preserves an ancient cratered surface with minimal geologic activity. Together, these worlds demonstrate how energy, gravity, and composition can combine in different proportions to create varied outcomes within a single planetary system. As time passes, Jupiter's atmosphere circulates and evolves. but the basic patterns of belts, zones, and storms remain as long-term features. Its magnetic field continues to trap charged particles and drive auroras. Its interior slowly cools while maintaining the metallic hydrogen layer that underpins its dynamo. On still longer timescales, the Sun's changes become the dominant factor. Jupiter endures the brightening of the main sequence, the expansion of the red giant phase, and the transition to a white dwarf, retaining its identity as a large planet in orbit around whatever form the Sun takes. In this way, Jupiter holds a stable place in the overall structure of the solar system. It never ignites as a star, yet it exerts a strong influence on the dynamics, stability, and evolution of the system around it. It formed from the same material as the Sun, nearly had the mass to begin fusion, and instead became the largest planet, with a complex interior, a powerful magnetic field, and a diverse family of moons. Its long life continues alongside the Sun through all major stages of stellar evolution. In simple terms, Jupiter's role in the solar system is to be the dominant planet, a massive, enduring world that shapes its surroundings without becoming a second sun.